So in the previous class, we have discussed that we can represent any our 3D CAD model in the form of triangular surfaces. Okay, so here we could see that this is a one human structure, and that we are trying to, you know, represent by using some triangles. Okay, so there are a lot of triangles you can see, and uh, these this information related to this triangle, how this information is stored in our computer, or what kind of information is needed to represent these uh, these triangles in our STL viewer. Okay, so that we have discussed in our previous class, and I will be taking a bit of revision, or for those who are new, it will be a good thing for them. Okay, so yes. So in when we were trying to represent triangles in a space, we were seeing that we assume that we are seeing from uh, outside of the that particular surface. Okay, and then we are taking we are we are taking the first we are listing the vertices, then we are considering these vertices in counterclockwise direction. Suppose this is the triangle represented by three vertices, 0 0 0 0 1 0 0 0 1, and how we since we are having three vertices, students, is there any noise issue? I hope everything is fine. Any one student, can you hear any noise? Everything is fine now? Yes, okay. So yeah, okay, so you can ask in between question. There is no problem, because from previous class we are taking a bit topic which require discussion as well. Okay, so if you have any query in between, you can interrupt in between. No problem. Okay, so this is the triangle. How we are trying, how we were trying to represent this triangle in a space. First, we need to have coordinate of these vertices, and since there are three vertices, 1, 2, 3. Okay, and the coordinates, corresponding coordinates were 0 0 0 0 1 0 and 0 0 1. So how we will store these the data corresponding to these vertices, or in which order these vertices need to be saved in a STL file that we have discussed in our previous class. Okay, so how do we store, what is the sequence? So the sequence we follow, that we need to list these vertices in counterclockwise when we are seeing from outside. Okay, so here since we are seeing from outside, so this will be your counterclockwise direction. Okay, so in counterclockwise direction, what will be the order? 0 0 0 0 1 0 0 0 1. Okay, this is the first. This may be one kind of representation, or you can do you can start from vertex 2, then it should be this is 1 2 and 3, then this should be 2 3 and 1, or 3 1 2, whatever fashion, or whatever the arrangement you like, but it should be in the vertices should be listed in counterclockwise direction. Okay, yeah. So this was the one example that we took in the case of tetrahedron, that how triangles in or the triangular facets in your tetrahedron are represented. So here we were having four surfaces. Since this photograph is again not clear, let me show again from the Chrome I have shown in the previous class in the same way. Okay, so in the tetrahedron in the case of tetrahedron, we have four surfaces A, B, and A, B, C, and D. Okay. Yes. Just a second. Yes, Chrome has come. Tetrahedron. Yes. Yes. For more clarity, we can take this way. Okay, so here we can see how many surfaces are there, 1 2 3 and 4. Okay, 4 behind this. Okay, so in any tetrahedron we have four surfaces, and these surfaces are triangular in nature. Okay, so suppose if we are seeing this particular surface from outside, then what will be the sequence? We need to you know mention these vertices, like suppose this is top left one is it is your first, then this is your second, then this will be your third, and even you can start from 2 3 1 like this. Okay, so this way we have uh, four triangular surfaces in the case of a tetrahedron. And how this tetrahedron surface need to be, uh, uh, the data needs to be saved in a STL file that we took one example. Okay, let me open it again. Demo, which we took on the last Monday perhaps. Okay. Yes. So here we could see the kind of information that is stored in STL file. We have solid name. Suppose we have solid tetrahedron. Then we need to give the data corresponding to your triangle 1, triangle 2, triangle 3, and likewise we have to continue. Then end of solid name. Okay, so each triangle has 7 lines. What are these 7 lines? Let me so yes, yes. So in each in the data corresponding to each triangle, we have these 7 line: facet, normal, 0 0 1. Then we have outer loop. Yes, so this is outer loop start and this is outer loop end. Then we have vertices corresponding to that particular triangle. So we have vertex 1, vertex 2, vertex 3. 1 2 and 3. Okay, so yes, so this is an example that we have discussed in our previous class, that we have this is corresponding to a solid tetrahedron. So solid name tetrahedron. Then we have these 7 line. Okay, in these 7 lines we have to represent the coordinates of your each vertices. Okay, so suppose corresponding to surface A, we have these 3 vertices: 1 1 0, 1 minus minus 1, minus 1 1 0. Then this data corresponding to another surface B, then data corresponding to surface C, then say, triangular surface C, then corresponding data corresponding to triangular surface T. Okay, so using this this data, we have entered this data in a text file. Here we have entered in a text file and saved this text file as STL. Okay, so this file we have saved as STL. Okay, and now we will open this STL file using some STL viewer. So let me open it with see we can try with 3D viewer. Okay, so here you can see this uh, this tetrahedron is represented in graphical form. Okay, so from your textual data, that is the data which you were having corresponding to this text data, we could see, we could draw a tetrahedron in our STL viewer. Okay, so this is how the data is stored in STL file, and this we have discussed in our previous class. So now we will come to the next part of our today's discussion. Okay, so in today's in the previous discussion, we could finalize that we can store, how we can store the data, and how we can divide the a complex 3D CAD file or solid part that is created in any of the CAD modeling software. We can directly import that particular data into a STL file. Okay, so up to this we have discussed in previous class, and now in today's discussion, that how we will slice this solid data. Okay, or the solid part, how we slice the corresponding CAD model. Okay, so in the user part, we have seen that we were using some slicing software, like let me open slicer 3D, slicer 3. Okay, yes, it is here. Yes, just a second, it is opening. Yes. Okay, so here what we were doing, we were exporting our STL file, let me open this example which we took in the first day. Okay, let me scale it by 75. Okay, yes. So this process we have done in our earlier classes also. Okay, but we were trying to see that what actually is happening when we are trying to slice a 3D CAD model. Okay, so let me show here. We have yes. Okay, so here we can see the when we are slicing our data, or when we are slicing our 3D CAD model, simply it is getting, it is getting converted into 2D contour. Okay, instead of 3D contour, we have 2D contour. Okay. Yeah, it is taking some time that it get open. I am trying to open Cura because I have explained earlier in Cura, so we can continue with the same software. Okay, no problem. It is not responding. Let it take some time. We can continue our lecture. No problem. Okay, so in slicing technique, we have three kind of technique, that is STL based slicing, then direct slicing, then slicing through slicing software. Okay, so like since we in all additive manufacturing processes, the important step is the conversion of your CAD model into your STL file, and then the next important step is your slicing of your STL file, or the CAD model. Okay, So in slicing, how we are slicing our slicing means we are converting our 3D CAD model into a thin layer of 2D part. Okay, and we are converting, we are getting the contour of 2D file. Okay, so yes. So how we can slice these uh, these uh, these STL file, that we will try to see, because through software it looks quite easy. Yes, Cura is open. Yeah. If you try Cura and let me open this part, it will look that it is very easy process. But we have to understand what is going on behind this slicing technique, and the information that is being presented here. Okay. Yes. So here this is our STL file that we have extruded. Now we can simply use cancel. Okay, we can. Here we can change the our sliced our layer height. Okay, so suppose for this model I have taken zero point 0.3, right? And yes, then slice. Preview. Okay, so we can see here, it is, this process is looking quite simple, that we have sliced this particular 3D CAD model into as per our desired layer thickness. Suppose I have chosen zero point 0.3 layer thickness. Okay, 0.3 mm. Okay, so since we are doing it by using the software, it is looking quite simple thing. Okay, we can easily do the slicing through this particular software, 3D view, right? Okay, and I guess I have shown that how this data is layer is getting printed. Like, let me play this layer. So here you can see how this printing is taking place. Okay, so I guess this process is looking very simple, isn't it? Students, are you hearing or not? Nobody is there? Yes. So because it is looking like that, we need to create only 3D CAD model. Okay, so those students who are from mechanical engineering background, they will say that, or civil engineering background, they will say that we need to create only 3D CAD model, and then we can convert that model into STL file. It is quite easy because ready-made software are available. Then we can slice this CAD model using any of the STL slicer, and then we can simply print our STL this slice data using any of the printer available in the market. Okay, so but at the from the point of user, it the process looks quite simple. Okay, But from the point of from the point of a technocrat or a mechanical engineer or a developer, okay, for whom it is necessary to understand the basic mechanism going on in the slicing. Okay, so what is going on in the case of slicing? Okay, because we were saying that we are storing this information in the form of triangular surfaces. Okay, so what happens? So what actually happens in the case of these triangular surfaces when we are slicing our 3D CAD model, because we are representing our 3D CAD model using these triangular surfaces. Okay, so how we will be slicing our CAD model, that we will continue our discussion here now. Okay, so an STL model is sliced by intersecting it with horizontal slicing plane, and each of which gives piecewise linear contour of a layer. Okay, so this we could see that in each of uh, in each of your slice layer, we are getting linear contour of your data. Okay, so here we are getting you have some linear contour. This is the linear contour corresponding to your one layer data. Okay, so this information we are getting after slicing our STL file by a horizontal slicing plane. Okay, so suppose at this slice this layer number 180, suppose I am talking about, suppose 187 I am considering this particular layer. So the this surface is, or this 2D contour is representing the data corresponding to your layer height, or the layer number 187. A slice of complex object may have group of contour, and each group may have multiple internal and external complex contours. The contours of a slice are distributed in a random manner without any no non-topological hierarchical relationship. Okay, so suppose let us take the an example at finite level, because we were saying that we are saving the information in the form of triangular facets or triangular surfaces. So suppose we were having surfaces like this, then another connected surface like this, then this. Okay, then triangular surface, some more triangles may be there. Okay, so there may be lot of triangular surfaces or the facets connected to each other, which are forming a solid CAD model. Okay, and suppose we have we let us consider one triangular element, one facet, which is represented here. This is vertex 1, then vertex 2, and vertex 3. Okay, and this is our whole slicing plane, which is slicing this particular triangle at point uh, P, and the coordinates corresponding to this point P are xp, yp, and zp. Length of this path, that is distance between vertex 1 and 2 1 and 2 is it is equal to L. Okay, so the coordinates corresponding to these three vertices are v1 v2 v1 x1 v2 v1 y2 sorry v1 x v1 y v1 z. Then coordinates corresponding to vertex 2 are v2x, v2y, v2z, and similarly for vertex 3 the data is v3x, v3y, and v3z. Okay, so here we will see how this slicing is taking place, and how this coordinates of point P are calculated. Okay, so suppose we are considering that the horizontal plane is intersecting at point x at point p, and the coordinates are xp, yp, and z. So we can easily see this relationship from the trigonometry, that the xp minus v1x upon v2x minus v1 is equal to yp minus v sorry yp minus v1y upon v2y minus v1y uh, is equal to zp minus v1z upon v2z minus v1 equal to t, and where t may vary from 0 to t may vary between 0 to 1. Okay, how many of the student, any student who is able to understand that this expression is simple representation of a trigonometrical concept, that these vertices will be forming similar triangle like v1 uh, these vertices, and the plane at which the point, this point is cutting this or the at the point this slicing plane is cutting your vertices, these will make similar triangles. So are you able to understand this expression or not? Any student, are you able to understand this expression, or let me elaborate it? Yeah, I could understand. Okay, so let me take you know one blank slide. Okay, let me try here. So suppose we are having vertex 1. Let me try with a simple triangle so that you can understand easily. Yes. Suppose this is vertex 1, vertex 2, vertex 3. Okay, and yes, and this is the point of intersection, right? So yes, because we are considering in between a vertex 1 and 2. Okay, so this is your point P, right? And now try to see, suppose this is forget about because we are considering two. Let me make more simple arrangement. Suppose this is our O, this is your vertex 1, and this is your vertex 2. This is your our origin, this is x, and this is y. Okay, this is your vertex 1, this is your vertex 2, this is your, and suppose if a plane is cutting at this point P. So let us try to understand only in 2D coordinate system, then you can explore it for 3D. Okay, so if you take this let us make this is x1 y1, okay, and this is x2 y2. Okay, and this is the corresponding coordinates xp, yp. So according to this expression, what should be what should be the expression for this? This should be xp minus x1 upon x2 minus x1 is equal to yp minus y1 upon y2 minus y1. Okay, and this should be equal to some constant k. Okay, suppose let it write as t. Okay, so let us try to see what is this xp minus x1. So xp minus x1, it means this would be uh, let us make triangles from origin. Okay. Mhm. Okay, so yes. So this will be xp minus x1, and this will be the data corresponding to this will be xp minus x1 and x2 minus x1. Okay, and we will try to see for this z value in you know but in the similar fashion. Okay, hello. Yes, okay. So this way we can we can see this relationship, because these three vertices, and this relationship has been obtained by the concept of similar triangles. Like here p x y, and these will be making similar triangles, right? So the value corresponding to this, you know, like suppose we write d1, and suppose we write as d2. Okay, so d1 upon d2, like in similar triangles, this property exists there, na. One d1 upon d2 equal to constant. Okay, similarly suppose this l1 and this is l2, so then this will be equal to d1 upon d2 will be equal to l1 upon l2, right? So this is how this expression has been calculated. Okay, this as expression has been elaborated here. Okay, so for three dimensional case we can explore in terms of z axis too. Okay, so that is why it is written as zp minus v1 z divided by v2 z minus v1 z equal to t, because these three the ratio of all these three will be constant as per the properties of your similar triangle, right? So yes, yeah. So now since we here we have one slicing pair, and we are we are slicing our triangular facets, or our STL data through this slicing pair. Okay, now we will try to see what are the slicing approaches, how this slicing takes place. Okay, so suppose we are having this particular surface which is represented here. This is our actual contour of the surface, which we are supposed to you know which we are supposed to slice using our this particular algorithm, or the concept. Okay, so one concept is top down slicing approach. Okay, so we will try to see what is our top down slicing approach and what is the bottom bottom up slicing approach. In the top down slicing approach, what we are doing, since this is our data or the our contour of our actual surface, and what we are doing, we are slicing. Since we are slicing this data, we will have some slicing plane, something like this. Okay, so in top down slicing approach, what we are considering the top vertex of each intersection point. So suppose at this point we are considering this, then at this point we are considering this, then at this point, at this layer we are considering this layer, then at this point we are considering this. We are always considering the top vertex of your contour data, 2D contour data. Okay, so this is our top down slicing approach. Then we have another type of slicing approach, that is the bottom up slicing approach. So suppose we have this layer. In the try to see the difference in these two slicing strategies. Like this is our surface module, and in this layer, which data we are considering? We are considering the top vertex data. Here also, which data we are considering? We are considering top vertex data, which is corresponding to this layer. Then corresponding to this layer, we are again considering top data. Corresponding to third layer, we are considering the top vertex data. Okay, so in the case of bottom up slicing approach, which vertex data we are supposed to consider? We are supposed to consider the bottom data. Okay, so suppose these are the layers, and this is our this is our actual contour of your surface. Okay, and in the bottom approach, since we are considering the bottom vertex data, so suppose if you are taking layer 1, which vertex you will consider? You will consider this. Okay, but in earlier version, the which vertex was considered? For layer 1, this vertex was considered. Okay, so this is the difference, that instead of in the bottom up slicing approach, we are considering the bottom line data. Okay, so the data corresponding to this or the intersection point corresponding to this value will be considered. Then for the second layer of your data, which value will be considered? This vertex will be considered, right? So this is how this bottom up slicing approach or the top down slicing approach works. So or the corresponding data is saved, or the vertexes are saved. So in the bottom down, we are seeing something like this. Okay. Yeah. Yes. So now in these, what are the issues in these two datas? Okay, these two slicing approaches. Okay. So when here you can see, when this slope is something like this. Okay. Let me show it again in top down slicing approach. Okay, so what is happening when we are considering only top vertices? Here we can see when this layer is getting printed, it is printed based on this upper vertex data. Okay, and again since we will print from bottom side. Okay, so for this layer, this data up to this will be printed. Okay, and for this layer, because for second layer where data from bottom side, we consider 1 2 3 4 5 6 7 8. Suppose these are 8 layers. Okay, so for this because for in the top down slicing approach, we are considering data corresponding to top layer. Okay, so up to this point, this material will be printed up to this point, right? For second layer, how much material will be printed? Because second layer, the upper vertex is at this point, so the material will be printed something like this. Okay, then let me make it with another color, so that yes. Then color. Yes, so I am changing the color because so that you can understand the issue which I am trying to make you clear. Okay, so because for this layer 1, because we have to print the material from always material will be printed from will start from your bottom up side. Okay, so here you can see, because we have sliced the data using the top down slicing approach, it means we are considering the top vertex data. So what will happen, your material will be printed up to this point. Okay, so suppose this is our finally printed component. For layer 2, again we have a top down slicing approach. So the data corresponding to your tool or the your machine or the printer will print the data corresponding to this particular layer 2. Okay, so here we can see there is, excess printing of, excess material is getting printed in this portion. Okay, so similarly we will continue to the layer 3. Okay, uh, again here excess material is getting, is coming out of your part geometry. Then again corresponding to your part 4, sorry, layer 4, then corresponding to layer 5. And now here you could see some extra material was coming. And now here suddenly what you will notice beyond this layer 5, because it will take data corresponding to this particular vertex. So material will be printed up to this point only. Okay, then for layer 7, this will take data corresponding to this vertex, and the material will be printed up to this point only. Then corresponding to this okay, so here we can see in some portion some extra material is getting deposited and some portion is remaining vacant. Could you notice it? Okay, so the similar thing is happening with the bottom up slicing approach. Okay, in the bottom up slicing approach, here because we are considering since the bottom vertexes, here some material is not getting printed, it is not getting filled in some areas, and in some areas the extra material is getting printed. Okay, or there is excess deposition of your material data. Okay, so in these two slicing strategies, what is happening in top down approach, when the slope negative slope, when slope is negative, it will it will result into the undersize. Suppose because the slope is negative, this slope is negative, so it is resulting into the undersize, and you are not able to get your appropriate profile, or your there is, you can say, shrinkage in the size of your component to be printed. Okay, but when this slope is positive, then this excess material is getting printed, or you can say there is oversize an oversize in the part which is being getting printed when you are considering when you have sliced your model using your top down approach. Okay, then similarly in the case of bottom up approach, what is happening, the reverse is happening. Negative slope is resulting into oversize, or your because this is your negative slope, and this is resulting into oversize of your component. Again positive slope is resulting into undersize. So this type of things happen in the case of model slicing, when we are slicing our model using our these two approaches. Okay, so there are some other issues that I hope we can discuss these issues in the next class. For today I will stop here.